During structural analysis, engineers often have to choose between sections. As you must know, beams comes in different sections in civil engineering, which include rectangular, circular, L, T, and I sections. So how do engineers actually choose between sections based on their strengths? Today we are going to be delving into a formula that helps engineers to serve this purpose. After our calculations, we are going to go ahead to a software program to correspond our answers. Before we dive into the formula, we have to talk about a very important concept in civil engineering, the neutral axis. So let's say we have a beam which is simply supported, and let's say that this beam is divided into a number of layers. If you apply a load on the beam, all of these layers will bend. But the layers towards the top of the beam will be under compression, and the magnitude of compression will decrease downward, while the layers towards the bottom of the beam will be under tension, and the magnitude of tension will decrease upward. Then there must be a layer which is the meeting point of these two effects, and which is neither under compression nor tension, hence the name neutral axis. You can also dub this axis the origin, where compression and tension is 0,0. Now let's move on. The formula you see on the screen is called the bending equation, and it helps engineers to determine the strength of beams. The M in the expression is the maximum bending moment or the moment of resistance of the beam. The maximum bending moment is due to the load, and the ability of a beam to resist this bending moment is called the moment of resistance of the beam. So for equilibrium, these two has to be equal, and that means the higher the maximum bending moment, the stronger the beam. The figure below gives the bending moment diagram for a beam under a uniform distributed load, and the maximum bending moment is given as WA squared divided by 8, which is the point of the orange arrow. The second picture gives an example of a typical beam, and whatever shape you see at the point of the arrow is the cross section of this beam, and for this particular beam, it's a rectangle. The Y in the expression is the distance from the neutral axis to the outermost layer of the cross section. Also take note that the neutral axis coincides with the centroidal axis. So for a rectangular cross section, Y is just half of the depth. The I in the expression is the moment of inertia of the cross section about the neutral axis. Y sigma is the maximum stress on the beam due to the load. E is the Young modulus of the material making up the beam. And lastly, radius of the curvature of the beam after bending is symbolized by R. But for this particular video, we will not be working with E and R, so we are going to focus our attention on the rest of the parameters. Now this is what we have. Since we have already established that the maximum bending moment must be equal to the moment of resistance of the beam at equilibrium, why don't we express M in terms of other parameters? If you do that, another parameter will pop out, the section modulus. So the section modulus is just the ratio of the moment of inertia to the distance of the outermost layer from the neutral axis. With that, you can express M in terms of sigma and Z. Since sigma is dependent on the load, what then determines the strength of sections? I guess you know the answer to that. Since Z is equal to I over Y, then let's go ahead to compare the strength of the following sections. Now for all rectangular sections, I is always the product of the width and the cube of the height divided by 12, and Y is just half of the height. Now if you go ahead and plug all your values from the diagram, you're going to get your height to be 208,333,333.333 mm to the power of 4. And then your Y is going to be 25 mm. Since section modulus is the ratio of these two values, you get your Z to be 83333.333 mm to the power of 3. As we have noticed, the second rectangular section is similar to the first, only that we have switched the values of W and H, but the formula remains the same. So I in this case will be equal to 50 multiplied by 200 cube divided by 12, and then you are going to get this answer. Y is going to be equal to 100 because now height is 200. So if you go ahead and find the ratio of these two values, you are going to get Z to be equal to 333,333.333 mm cube. Now lastly, for the circular section, the formula for Y is given as pi multiplied by d raised to power 4 over 64, where d is the diameter of the circle, and Y is just the radius, d over 2. With a diameter of 200 from the diagram, I can be calculated as 785,398,16.34 mm to the power of 4, and then Y is equal to 100 mm. If you take the ratio of these two values, you are going to get Z to be equal to 785,398 per 1634 mm cube. From these three answers, we can conclude that The circular section is the strongest because it has the highest magnitude for Z, then followed by the second rectangular section, and then lastly, the first rectangular section is the weakest because it has the smallest value for Z. Let's go ahead to software to test what we just did. I'm using robot structure analysis, so I'm going to click on axis definition at the top right corner of my screen here, so I can create a grid for my work to be easy. On the x-axis, I'm using a repeat of 2, and the repeat is 1 meter. That makes a total distance of 2 meters on the x-axis. I'm going to click on add. On the y-axis, I will do the same. On the z-axis, I'm just going to use 1. Then click on apply, close this. You can click the home icon here to see the 3D view. Now let's go ahead to model the sections we used in the example. So click on member section here and then click on this new section definition icon. Make sure parametric is selected here and also select rectangular from the list of options here. Because we're working with solid section, so mark this solid button, then input your dimension, which is 200 by 50 for the first rectangular section. Pick any color you want from the list, click on add. For the second rectangular section, change the label, just switch the value. We have 50 here, and then we have 200 here. Click add. For the last one, which is the circular section, click on 2. Once again, we are working with solid section, so click on that. Then the diameter is 200. Change the color, then click on add. You can then close this. Now find members at the right side of your screen. As you can see here, you can select the member type that you want. Because you are dealing with beams, select the beam, and then section, click on section. As you can see, the section we created have automatically appeared here. So select this first rectangular section and put it here. Go back and select the second rectangular section. Then lastly, the circular section. Let's add some support to the beams. So click on support at the right side of your screen. Then select pinned support. Then close this. Now click on load types at the right side of the screen. Under nature, make sure date is selected. Then click on add. The first date load symbolized by DL1 is the self weight of the 3 beams. So click on add again for a second date load, which are going to apply value to over the length of the 3 beams. So close this. Now find load definition just below load types, and then go to member because we are working with members. Select uniform load. Because you want to apply a load vertically downward, input negative 70 or any value you want in the Z column. So click on add. Go to apply to. Select all the 3 beams by clicking on the right side of the screen, then dragging it up. Click on apply. Close this. Then click on calculation at the top here. Click yes, and then press escape to get rid of all the warning. The program is telling you that your structure is separated. So go to results to find diagram for members. Go to deformation tab and take exact deformation for members. Now click apply. Then you can close this. At the bottom left corner of the screen, look for section shapes to either turn on or turn off the shape of the section. You can see here that the 200 by 50 rectangular section is giving us the most deformation of 34, and the circular section is giving us the least amount of deformation of 1. You can see now that this is proof that our section modulus calculation is correct. Right click on the circular section and go to object properties. Go to properties. Under section properties, you can see our calculated value for moment of inertia here. These 2 other values are also I values but along the X and Y axis. Do the same for the other 2 sections. You can see our values here. This is how software can help you with the calculation, but I think it's best that you know what is going on.